Hi everybody, today we're going to talk about exponential growth and decay in modeling problems. A substance that grows every second of every minute of every day is said to grow continuously. Continuous growth affects population. That could be for a city, a state, or an entire country. But continuous growth does not only apply to people. We can use it to model populations of animals, insects, and bacteria. The equation we use for continuous growth is A equals A naught e to the kt. A naught is the initial amount that we're starting with when time is equal to 0. A will be the amount we have at some time t. K is the growth or decay rate, and then t is the time. And we really want to pay attention to the unit of time for the particular problem we're solving. Sometimes this is also written as A equals PE to the RT, where P is the principal or starting amount, A is the amount at time t, R is the rate of growth or decay, and T is still the time. Growth versus decay is related to the sign of K. When K is positive, the function is growing. When K is negative, the function is decaying. Let's use this information to solve some problems. We'll start with the population in Europe was 736 million in 2010 and was growing at a rate of 0.2% per year. Let's estimate the population in 2035. Our first step is to write the growth rate. I'm going to use R for this problem. I have R equals 0.002. Then I know my initial amount was 736. When I put that into the formula, A equals A naught e to the RT, I have A equals 736 e to the 0.002 t. T will be the number of years between 2035 and 2010. That means T is 2035 minus 2010, which is 25. Now I can plug the 25 into my equation, which gives me A is 736 e to the 0.002 times 25, which is about 773.74 million people. Using the same information, let's estimate when the population of Europe will be 800 million. We'll give our answer as a year. The first thing I'll do is bring back my equation. A is 736 e to the 0.002 t. We want to solve the equation when A is equal to 800. Now I have 800 equals 736 e to the 0.002 t. To solve this exponential equation, I'll divide both sides by 736. Then I'll apply the natural log to each side. This becomes the natural log of 800 over 736 equals 0.002 t. I divide by 0.002 to get my value of t. T is about 41.7 years, but because we want to give the answer as a year, I'm going to round that to 42. 42 is not our answer. Remember, our problem said t is the number of years after 2010. So to find our year, we'll add 42 to 2010, which gives me 2052. Our next problem says, in 2008, the population of Colorado was 4.93 million. In 2018, the population was 5.69 million. Assuming the growth rate is continuous, find the rate of growth for the state. We're going to approach this problem as 4.93 being our initial amount. We want to find the rate of growth for the state. Our time is the number of years between 2008 and 2018, and our future amount is 5.69 million. We need to solve the equation 5.69 equals 4.93 e to the k times 10. Just like we did when we solved exponential equations, we'll use our process of divide, log, divide to find our solution. I begin by dividing 5.69 by 4.93, which gives me e to the 10k. Then I'll take the natural log of each side. On the left, I still have the natural log of 5.69 over 4.93, but I know that the natural log of e to the 10k is just 10k. To get the value of k, I divide the natural log of 5.69 over 4.93 by 10, which gives me 0.014. This is equal to a 1.4% growth rate. Now that we looked at a few problems that talk about growth, let's take a look at decay. We're going to start by talking about half-life. Half-life is the time needed for our initial amount to be reduced by half. That means when A is equal to half of A naught. We'll start with a small example. The half-life of Seaborgium 266 is 30 seconds. If you start with 0.16 milligrams, find the number of milligrams at the indicated times. This says every 30 seconds I should have half as much as I did the previous 30 seconds. Because we started with 0.16 milligrams, 30 seconds later, I'll have half of that amount. Half of 0.16 is equal to 0.08 milligrams. If I look 30 seconds later, which is a minute from my starting time, I'll again have half of my previous amount. Half of 0.08 will be equal to 0.04. If I add another 30 seconds, which makes it 90 seconds altogether, I now have a half of 0.04, which is equal to 0.02. If I look at 2 minutes from my beginning time, I'll now have half of my previous amount of 0.02, which is 0.01. This shows us the continued multiplication of 1/2 times the previous amount for every half-life that we encountered. To help us solve half-life and doubling time problems, I want to give you two equations. The first equation says the half-life of a substance can be found using the equation T equals the natural log of a half over R. I want you to see the connection between half-life and the 1/2 in the equation. The doubling time can be found using the equation T equals natural log of 2 over R. Again, look at the connection between doubling time and the number 2 in the equation. That should help you determine which equation to use in your problems. I also want you to remember, when we're using half-life, the R should be negative. When we're looking at doubling time, the R should be positive. Half-life is decaying, doubling time is increasing. Let's use that equation to find the doubling time. We're given the population of Las Vegas is growing at a rate of 3.67%. How long will it take for the population to double? We're going to use the equation T equals natural log of 2 over R, where we write the R as 0.0367. This gives us a time of 18.89 years. Notice I didn't need to know the current population of Las Vegas to find the doubling time for the city. Our next problem says a bacteria in a petri dish is growing at a rate of 7.25% per hour. How long will it take for the bacteria to double? Notice that the rate of growth this time is given in hours, not years. We use the same formula, T is equal to the natural log of 2 over R, and we plug in our rate as 0.0725. When we put that in our calculator, we get that the time is 9.56 hours. Let's take a look at half-life. The rate of decay of a plastic bottle is 0.0015. Find the half-life of a plastic bottle. Because we're looking at the half-life, we use the formula T is equal to the natural log of a half over R. Remember, R is negative. When I plug in the 0.0015, I use T equals the natural log of a half over negative 0.0015. Putting this in our calculator, we find that the half-life of a plastic bottle is 462.1 years. We're given the half-life of a plastic bag is approximately 20 years. Find the rate of decay of a plastic bag. In the previous problems, we solved for T. This time we're given T, and we need to find R. We use the same formula, the natural log of a half over R is equal to T, and we plug in that T is equal to 20. To solve this equation, I move the R to the left, I move the 20 to the right, which gives me the natural log of a half over 20. I put this in my calculator, which gives me R is about negative 0.0347. Our next problem says the half-life of silicon-32 is 710 years. If 30 grams is present now, how much will be present in 300 years? Round your answer to 3 decimal places. The 32 attached to the silicon is part of the name of the substance we're looking at. You don't use the 32 in the problem. We start by finding our rate of decay. This is equal to the natural log of a half over our half-life of 710 years. That comes out to about negative 0.00098. We'll use this rate along with our initial amount of 30 grams to estimate the amount of substance that will remain when T is equal to 300. We have A is 30 e to the negative 0.00098 times 300. This gives us about 22.56 grams. Our last problem says a fossilized leaf contains 15% of its normal amount of carbon-14. Use 5,600 years as the half-life of carbon-14. How old is the fossil? We'll start by finding our rate of decay. R is equal to the natural log of a half over our half-life of 5,600 years. This is equal to negative 0.00012. We don't know our initial amount, but we know the future amount is 15% of whatever the initial amount should be. This means I have 0.15 times A naught is equal to A naught e to the negative 0.00012t. To solve for t, I would first divide by A naught. 0.15 A naught over A naught is equal to e to the negative 0.00012t. The A naughts are going to cancel, then I can apply the natural log to each side. Now I have the natural log of 0.15 is equal to the natural log of e to the negative 0.00012t. We know the natural log and e work together to bring that exponent down. This gives me natural log of 0.15 equals negative 0.00012t. My last step is to divide by the negative 0.00012. The natural log of 0.15 over negative 0.00012 gives us t. This is about 34,997.54, which we would realistically report as 35,000 if we were outside of an academic setting. There are many other applications to explore. I'll have additional videos that go over logistic growth models and Newton's law of cooling.